Hi, welcome to ACE Online. Myself Krishna Reddy, Faculty of Electrical Engineering, Power System topic. So here we are going to discuss about power transfer equations in case of transmission line. So before going into the details of power transfer equations, let us observe here. So the power generation is going to take place at the remote place. If we observe the hydel plants or thermal plants, they are located at remote place. So whatever the power that is being generated is to be transmitted using the transmission line. So here the sending end voltage is Vs at an angle of delta, and the power is being transmitted using the transmission line. Let the receiving end voltage is Vr at an angle of 0. Here the loads are connected at the end. How do you write the complex power equation at the receiving end? So what will be the complex power at the receiving end? So how do you write the complex power equation? Complex power at receiving end. So what will be the complex power at the receiving end? SR is equal to VR into IR conjugate. VR into IR conjugate. So what is the purpose of this conjugate here while you are writing the complex power? So why the conjugate is required here? The purpose of the conjugate is to ensure the sign for real power is always positive and the sign for reactive power changes based on the load condition. Okay. So as we know the two-port network equations, so by using the two-port network equation, let us try to establish the relation for what? The receiving end current. So the transmission line can be represented using two-port network parameters, that is nothing but ABCD parameters. So we can write the sending end voltage Vs is equal to AVR plus BIR, okay, two-port network equation. Vs is equal to what? AVR plus BIR. So in polar form, how do you represent? In polar form, representation of ABCD parameters will be A is represented as mod A at an angle of alpha, B parameter is represented as mod B at an angle of beta, C is represented as mod C at an angle of gamma, D is represented as mod D at an angle of alpha. So this is a polar form representation of what? ABCD parameters. And the sending end voltage in polar form is Vs is mod Vs at an angle of delta, and receiving end voltage is mod Vr at an angle of 0. So these are the polar form representations. Now, so we got Vs is equal to, sending end voltage Vs is equal to AVR plus BIR, AVR plus BIR. So from this we require the receiving end current IR, so in order to get the complex power. So IR can be written as what? Vs minus AVR by B, Vs minus AVR by B, okay. So from this equation I have written the value of IR. So Vs is what? Here you can write IR as Vs is mod Vs at an angle of delta minus mod A at an angle of alpha, mod Vr at an angle of 0 by mod B at an angle of beta. So this is the equation for receiving end current. So now let us try to simplify this and write the value. Receiving end current IR can be written as what? Here Vs by B at an angle of delta minus beta. So Vs by B at an angle of delta minus beta minus A by B Vr at an angle of beta alpha minus beta. A by B Vr at an angle of alpha minus beta. So this is the receiving end current. But here while calculating the complex power, we require IR conjugate, okay, IR conjugate. So how do you write the conjugate of this current? So complex power SR is equal to VR into IR conjugate. So VR into IR conjugate is, take the conjugate of that. So Vs by B at an angle of beta minus delta minus A by B VR at an angle of beta minus alpha. So this is the equation for what? Complex power at the receiving end. So still if you multiply with VR, so finally we will get the complex power SR is equal to Vs VR by B at an angle of beta minus delta minus A by B VR square at an angle of beta minus alpha. So this equation gives the complex power, okay, at the receiving end. Now from this complex power equation, we can write the value of real power at the receiving end and the reactive power at the receiving end. What is the real power that has been transferred and what is the reactive power that has been transferred, we can get from this equation. So what is the real power transfer equation? Real power at the receiving end, PR is Vs VR by B cos of beta minus delta minus A by B VR square cos of beta minus alpha. Okay. So this gives the real power at the receiving end. Vs VR by B cos of beta minus delta minus A by B VR square cos of beta minus alpha. So this is the real part of this equation. Okay. This will give the real power in what? Megawatt. Okay. This gives the real power transfer in megawatt. What about the reactive power transfer equation? QR is, so Vs VR by B sine of beta minus delta minus A by B VR square sine of beta minus alpha. So this gives the reactive power in MVAR. Okay. So these two are what the power transfer equations we can say. These two are the power transfer equations in case of transmission line. Now generally nobody will ask about these power transfer equations, but the question goes like this. What is the condition for maximum real power transfer at the receiving end? Okay. So what the question will be? So what is the condition for maximum real power transfer at receiving end. Okay. So what is the condition for maximum real power transfer at the receiving end? These type of questions can be asked. So when you can get the maximum real power transfer at the receiving end? That real power transfer, in order to get the solution for this question, so PR is a function of what? Load angle delta. PR is a function of what? Delta, load angle or power angle delta. So in order to get under what condition you can get the maximum real power transfer at the receiving end? Differentiate with respect to variable and equate to 0. Okay. So what we need to do? dPr by d delta equal to what? 0. So d by d delta of, so let us write the power transfer equation that we got. So here Vs VR by B cos of beta minus delta minus A by B VR square cos of beta minus alpha is equal to what? 0. Differentiate with respect to variable and equate to 0. So if you differentiate this with respect to variable and equate to 0, what do you get, sir, here? So Vs VR by B cos of beta minus delta is what? Sine of beta minus delta is equal to what? 0. Okay. So now only the term that you can equate to 0 is sine of beta minus delta is equal to 0. So what is your observation? When you will get the maximum real power transfer? when delta is equal to beta. So here, because whenever the load angle is same as, whenever the load angle is same as the impedance angle of transmission line, whenever the load angle is same as the impedance angle of the transmission line, you will get the maximum real power transfer to the receiving end. Okay. So this is the condition that must be satisfied. When delta equal to beta, you will get the maximum real power transfer at the receiving end. Okay. Load angle must be same as impedance angle of the line. So the question goes like this: what is the condition for maximum real power transfer at the receiving end? He will give one of the option as what? Delta equal to beta. Okay. So now, what is the PR maximum value? What is maximum real power transfer at the receiving end? What is the maximum real power transfer at receiving end? So how do you calculate? So here in this equation you need to substitute delta equal to beta. Cos 0 is 1. So remaining terms goes as it is. So PR maximum value is what? PR maximum is Vs Vr by B minus A by B Vr square cos of what? Beta minus alpha. So this gives the expression for maximum real power transfer at the receiving end. This is also known as a steady state stability limit. This is also known as what? Steady state stability limit. Stability limit. This is also known as what? Steady state stability limit of the. Now, that is the maximum power that can be transferred. Now, under this maximum power transfer condition, what will be the reactive power? Okay, what is the reactive power transfer? What is QR? What is QR under PR maximum condition? PR maximum, that is when delta is equal to beta. So what will be the value of QR when delta equal to beta? So here we got the reactive power transfer equation, So when delta equal to beta, this sin 0 is what? 0. Okay. Now only left out term will be this negative term. Okay. So what is the value of QR under that condition? QR is minus A by B Vr square sin of beta minus alpha. So this is the reactive power transfer under maximum real power transfer condition. So what is our observation here? The sign for reactive power is what? Negative sign. It is having what? Negative sign. So as it is having negative sign means, so it should be of what nature? Capacitive nature. Okay. Capacitive nature. Load must be of capacitive nature. That means it should inject the reactive power, or it should be of synchronous motor load. It should be of synchronous motor load, because synchronous motor can inject the reactive power. So it should be either of capacitive nature or synchronous motor load. But in practical case, we are not using synchronous motors. We are using what? Induction motors, because this synchronous motor has certain limitations. It is a doubly excited machine. It is not self-starting. It increases the fault level. It is associated with stability issues. Okay, all these are what? Limitations of synchronous motor. In practical case, most of the motors that we are using are what? Induction motors. So if we observe the power angle curve, that is variation of real power transfer with respect to load angle, it is a sinusoidal variation. So delta 0 to 90 degrees, this is the stable region of operation. Once it exceeds 90 degrees, it results in what? Unstable operation. Okay. Now, we are getting the maximum power transfer when delta equal to beta. this is the point where you are getting PR maximum. So for long transmission line, this is around 87 degrees. For long transmission line, the impedance angles will be very high because the reactance will be very high, X by R ratio will be very high. So the impedance angles are very high. So now if you are operating under this maximum power transfer condition, the stability region is narrow, stability region will be very narrow, okay. So if there is any disturbance created, it may result in unstable operation. If you are operating under what condition? Maximum power transfer condition. So we will not operate the system under maximum power transfer condition. We will be operating in a stable mode. That is, operating angle will be around 30 degrees to 45 degrees. So for stable operation, stable operating angle lies in between 30 degrees to 45 degrees, okay. So stable operating angle is around 30 degrees to 45 degrees. We will operate in this region, not under the maximum power transfer condition, okay, because if you operate at this point, it may result in unstable operation if there is any change in load. So for stable operation, where the operating angle lies between 30 degrees to 45 degrees. So now for further analysis, if you consider a short transmission line, then what will be the power transfer equations? So if you go for a short transmission line, what will be the power transfer equations here? So if an alternator is connected to a short transmission line, in case of short transmission line, what are the ABCD parameters? What are the ABCD parameters in case of short transmission line? 1Z01, okay, 1Z01. So A value is 1, so magnitude of A is equal to 1, alpha is equal to 0. For a short transmission line, magnitude of A is 1 and alpha is equal to 0. And magnitude of B will be under root of R square plus X square, and beta is tan inverse of X by R, okay. So now by substituting these equations, we will get the power transfer equations in case of short transmission line. A value is 1, alpha value is 0, okay. So now what is the receiving end power, real power and reactive power? Let us write for a short transmission line. So Vs Vr by B cos of beta minus delta minus A by B Vr square cos of beta minus alpha, alpha is 0. So this gives the real power transfer of short transmission line. What about QR? Vs Vr by B sine of beta minus delta minus 1 by B Vr square sine beta, okay. So this gives the reactive power transfer equation for a short line. Now let us check for a short line when maximum power transfer takes place. So when PR is maximum, that is when real power transfer is going to be maximum. So for that dPr by d delta equal to 0. Differentiate the real power transfer with respect to delta and equal to 0. So d by d delta of, so the real power transfer equation is what? Vs Vr by B cos of beta minus delta minus 1 by B Vr square cos beta is equal to what? 0, okay. So here what we get, Vs Vr by B sine of beta minus delta is equal to what? 0, okay. So now what is your observation? So from this the maximum power transfer takes place when sine of beta minus delta is equal to 0. So when delta equal to beta, so that is when load angle when load angle is same as the impedance angle of the transmission line. When load angle is same as the impedance angle of the transmission line, you will get the maximum power transfer. Okay. So now, what is the maximum power transfer? Here delta equal to beta, cos 0 is 1. So PR maximum value will be what? PR maximum is Vs Vr by B minus 1 by B Vr square, 1 by B Vr square cos beta, cos beta. This is the maximum power transfer equation. Now, what will be the reactive power under maximum power transfer condition? Let us observe here. This is nothing but the equation to calculate the steady state stability limit in case of what? Short transmission line. Now, if you consider what is the value of QR, what is QR under PR maximum, maximum real power transfer condition, that is when delta equal to beta. So what is the value of QR when delta equal to beta here? Now, whenever you substitute delta equal to beta, sin 0 is what? 0. So the term of reactive power is minus of 1 by B Vr square sin beta. Okay. So here also the sign shows that it is with a negative sign. Okay. Sign is negative. So in order to get the maximum power transfer condition, real power transfer, the load must be of what? Capacitive nature. Capacitive nature. That means it should inject the reactive power. It should supply the reactive power. Okay. Now, in order to continue further analysis, if you consider a lossless short transmission line. So let us observe here. If you consider a lossless short transmission line. So in case of lossless short transmission line, what will be the power transfer equations? So here resistance is 0, impedance is only reactance, beta will be how much? 90 degrees. Okay. So under that condition, what will be the real power transfer and what will be the reactive power transfer? Let us observe here. So here the PR value will be what? Vs Vr by x, okay, cos of 90 minus delta minus 1 by x Vr square cos of 90. Okay. So cos 90 is what? 0. So cos of 90 minus delta is sin delta. So real power transfer equation is what? Vs Vr by x sin delta. So you need to use this real power transfer equation at the receiving end, provided that the line is lossless. The line is lossless. And what is the value of QR under the condition? QR is Vs Vr by x sin of 90 minus delta, sin of 90 minus delta minus 1 by x Vr square sin 90. Sin 90 is what? 1. So from this, what is the value of QR that you get? QR value that you get is what? If you take Vr by x as common, so here Vs cos delta minus Vr, Vs cos delta minus Vr. So this is the reactive power equation. Whenever the line is what? Lossless. So provided the line is lossless, we need to use these equations for calculating the power transfer. So what is the maximum power transfer? When delta equal to 90 degrees, you will get the maximum power transfer. Okay. So when delta is equal to 90 degrees, you will get PR maximum. PR maximum is what here? Vs Vr by x. So if the line is lossless, if he has given the sending end voltage, receiving end voltage and reactance, we can get the steady state stability limit by using this equation. Okay. So from this expression, you can write the value of real power transfer as PR is PR maximum sin delta. Okay. So from this what you can write, PR is directly proportional to sine delta. So in stable region, that is 0 to 90 degrees, we can write PR is directly proportional to delta. That means real power transfer depends on the difference of angles between the buses. Real power transfer depends on what? Difference of angle between the buses. So for specific transmission of real power between the buses, there must be difference in what? Angles. And what about the reactive power equation that we got? QR, that is VR by X, Vs cos delta minus VR, Vs cos delta minus VR. So if delta is small, cos delta can be equated to what? 1. Okay. So if delta is very small, cos delta can be equated to 1. QR is VR by X, Vs minus VR. So what we can say, reactive power transfer is directly proportional to what? Difference of sending end and receiving end voltage magnitude. So for specific transmission of reactive power between the buses, there must be difference in what? Voltage magnitudes. Okay, this can be the conclusion. Suppose if you take two buses, V1 at an angle of delta 1 and bus 2 is V2 at an angle of delta 2. So if the question may be given like this, I want to transfer, this is bus number 1 and this is bus number 2. I want to transfer from bus 1 to bus 2. Real power transfer. What should be the condition that must be satisfied? Delta 1 should be greater than what? Delta 2. Okay. Bus 2 to 1, if you want to transfer the real power, delta 2 should be greater than what? Delta 1. Okay. Similarly, for reactive power transfer, for Q to transfer from bus 1 to 2, Q transfer, magnitude of V1 should be greater than magnitude of V2. And 2 to 1, if you want to transfer, reactive power transfer, magnitude of V2 should be greater than magnitude of V1. So that means for specific transmission of real power between the buses, there must be difference in load angles, and for specific transmission of reactive power between the buses, there must be difference in what? Voltage magnitudes. Okay, these sort of questions can be asked in the examination. Okay, so these are the power transfer equations that I need to put before you. So while you are using these equations, actually this will give the per phase power transfer. Okay, you should substitute the phase voltages. Okay, the voltages must be substituted as phase, then it will give the per phase voltage. If you want 3 phase power, multiply with 3. So with this I will conclude my session. You just have an idea about these power transfer equations, when the maximum power transfer is taking place, when load angle is same as the impedance angle, and what is the maximum power transfer condition, and what is the sign for reactive power under that condition, what is the operating angle range. So when it is lossless line, when it is the maximum power transfer taking place, and real power transfer depends on what, reactive power transfer depends on what. These type of questions can be asked in the PSUs. Okay, so thank you for giving me this opportunity.